Okay, please run now. The floor is yours.
Okay, can people hear me?
Yes, perfect.
Great. I'm delighted to be able to give my second lecture on primordial black holes. Here is a brief plan for my lecture today, and indeed Florian's lecture. I'm going to first of all continue the discussion of PBH constraints, which Florian begun yesterday. I'm then going to focus on more positively on the possibility that PBHs actually provide the dark matter. And I'll make some initial comments about that, but then I'll hand the floor over to Florian, who will be talking in much more detail of a particular natural scenario for PBH formation, which we're going to argue will explain a number of observations, what we call cosmic conundra. And that will, of course, include dark matter itself, which is the prime interest of this school. But then, bearing in mind that most of the audience are particle physicists, who might prefer the dark matter to be elementary particles, where Florian is then going to talk about the possibility that you have some combination of primordial black holes and particles providing the dark matter. And then there will be some final points, and I don't quite know how much time we'll have because it depends on how many questions you ask. You're very active in asking questions, which is good, but we have a few final points to make, and I will come in again then to make some final remarks as well. So let's start off then, continuing the discussion of PBH constraints. And I will start by showing the figure which Florian showed yesterday, which is a summary of the constraints on F, which is the fraction of the dark matter in primordial black holes as a function of mass. And all the coloured regions are excluded by various observations. And I'll say a little bit more about those observations today. I know that Florian didn't discuss these constraints in great detail, but the point he did stress was that there are only a few windows, mass windows, where primordial black holes would be allowed to have an appreciable density. He's talked about these already. These are labeled A, B, C, and D. And obviously, if you want the dark matter, in principle, you need F equals 1. So if you believed F had to be 1, it would look as though only A and D are possible windows. D isn't a window. I mean, D is what we call the stupendously large black holes, but they obviously couldn't make up the dark matter. They're too big to be in galaxies. So naively, you might think from this diagram, there's only one mass range where F could be 1. But as we'll see, you should treat that conclusion with caution.
Can I ask a quick question, please?
Yes.
Thank you. So we had previously argued that PBHs can't have a monochromatic mass spectrum, and yet it seems like we might like to situate all of them in this A range. Are those two ideas compatible with each other?
Now, wait a minute. I didn't quite hear you, but I think you're referring to the fact that this diagram assumes that the black holes have a monochromatic mass function. In other words, that the width of the mass function is of order the mass itself. So you do have to treat these limits with caution if you have an extended mass function, and that's one of the caveats. I think actually Florian stressed the fact that all these constraints have caveats, so you mustn't treat them too literally, that they could be weakened. Has that answered your question?
I think so. I believe previously we had said that these PBHs are not allowed to have a monochromatic mass function.
That's true. I mean, that is, well, it depends. I mean, that in the simplest scenarios, the black holes have a mass width, which is of order the mass itself. So if you like, delta M is of order M. And in that case, this picture is more or less correct. But there are other scenarios in which that isn't true. Now, if, for example, if you form from critical collapse, it's true you have a long tail, but it's still pretty well it's pretty good to approximate it as monochromatic because most of the mass is at one particular mass. I'm coming on to the extended mass functions later. By the way, can you give me your first name, because you ask lots of questions and I like to be able to address you.
Thank you. It's Anne Catherine.
Oh, that's quite complicated. Sorry, Jan. Anyway, thank you for your question. Now let me carry on. The point I want to make is that actually this diagram is itself taken from another diagram which I want to show, and this diagram is the work which I've done with my Japanese colleagues actually over many years. I spent quite a lot of my life compiling the constraints on primordial black holes. So this is a more complicated version of the diagram you've just seen. Again, it plots Fm against M. And it's got the same color coding as before, and it's got all these. I've labeled the constraints by acronyms. Now, I want to stress that the diagram is far too complicated to absorb, just by looking at it. But I'm really showing this diagram to give you an impression of really the huge amount of work and effort that has gone into getting constraints. Obviously, we would rather have positive evidence for primordial black holes, but until we've got that, the best thing you can do is to get constraints, because having constraints gives us important information about the early universe. But I don't want you, for example, I know that lady who asked questions, she could ask questions about any one of these constraints and it would take me an hour to go through them, but I'm not going to do that now. I think the French are famous because they invented Impressionism within the art movement. And so I'm really showing this diagram from an impressionistic point of view. If you want to understand the details of this diagram in more detail, I would refer you to the notes which Florian and myself have provided for the lectures, where these are discussed in more detail. However, I do want to say a little bit about them. So what I'm going to do now, I should stress incidentally that in the notes we accidentally included the old version of this diagram. So this is the new version. This is the new version of the diagram. These constraints which we're talking about are constantly changing. I mean, every week, every day almost, you have another paper coming out which changes them. So if you look over the history of this paper with the Japanese, it's gone through many iterations. This, what I'm showing now, will be the published version. The one in the notes was an older version from about a year ago. But let me say
there is a small question on the chat which says, why do you go with F larger than 1?
Oh, good point. Well, the reason for that is, I mean, obviously F can't be larger than 1, but it's interesting because these constraints evolve and they come with, they have error bars, they have sigma error bars and things like that. So it's interesting to see how the constraints will change with time. They can go up and down. So you're right, astrophysically you can never have F bigger than 1, but it's because of the error bars and the evolution of the constraints that we go a bit above that. But that's an important question. Thank you. Now, I thought, though, it would be useful to say a little bit about some of these constraints. So what I've done is I'm just going to talk about the lensing and dynamical ones. This is the blow-up of the lensing constraints, where we've got all the acronyms. And just so I'm not sort of, I just don't want to just show pictures. So here's a little bit of explanation of some of these things. The gamma ray GRB are the femtolensing constraints of gamma ray bursts. That's to say, you have a gamma ray burst and the primordial black hole goes in front of it and it causes a change in the luminosity. But the important point is that this is in the mass range 10 to the minus 16 to 10 to the minus 14 solar masses. Really small. It's quite amazing in a way that observations can be probing objects that small. But remember, they're bigger than the mass which would be evaporating. You can see the mass in grams on the bottom here. So they would still be around. But you'll notice these are dotted lines. And if it's a dotted constraint, that means we no longer believe it. So these diagrams are partly historical. So the dotted constraints we no longer worry about. Now, the HCS constraint, also shown dotted because it's been modified. HSC is the name of the instrument on the Subaru telescope, and they were looking for the microlensing of stars in M31. So the idea is you have a star in M31 and a primordial black hole either in our own halo or the halo of M31 goes in across the line of sight and it changes the luminosity. And again, that's put constraints in the mass range 10 to the minus 10 to minus 10 to the minus 5 solar masses. So again, these are very small. Objects this small could only be primordial. So this is the dotted line. If you look at the solid line here, I hope you can see my arrowhead, the share screen. The solid line is how it's been revised. So it's a little bit narrower than the dotted line. Now, Kepler, by the way, can someone say, do you see my arrowhead?
Yes.
You do, great.
Yeah.
So Kepler, that's the telescope, which was actually originally looking for planets, but this enables you to look for microlensing of stars in the galaxy. And this put constraints in the range 10 to the minus 9 to 10 to the minus 3 solar masses. So again, it's the colored region which is excluded. Ogle, which is a microlensing search, a Polish one, that looks at stars in the galactic bulge, and that puts limits in the range 10 to the minus 3 to 10 to the minus 1. These limits just correspond to where the curve hits f equals 1. Now, the old EROS, the French microlensing experiment, which goes back to the 90s, that was looking for microlensing of stars in the LMC, in fact, the SMC as well. Sorry, that's the Large Magellanic Cloud. And this is quite a precise limit, and it goes from something like 10 to the minus 7 to 15 solar masses. So this is the limit there. So these are now quite large objects. Macho, which was the equivalent project, was looking at a somewhat narrower range, 0.1 to 30 solar masses. So that's also shown, that's the little curve here. More recently, people have looked for the microlensing of supernovae. And there, of course, you're looking, these other searches are looking locally in the galaxy or Andromeda galaxy. This is looking at objects at cosmological distances. And there the limit goes from something like 10 to the minus 2 to 10 to the 4 solar masses. So that's that line here. And then at much larger scales, we have radio sources, and you've got the millilensing of compact radio sources. Now, the distinction between microlensing and millilensing is simply to do with the, if you like, it's the angular separation of the images, which is in microarc seconds for microlensing and milliarc seconds for millilensing. So, but again, you're looking for actual changes in luminosity. It's just that the bigger the lens, I don't think we've explained this, but the bigger the lens, the bigger the angular deflection. And so these are the radio sources. So I'm not putting any references in here. All of these limits have got dozens of papers. I refer you to the notes if you want the detailed references. And if any of you have written any of the papers connected with these limits, I apologize for not showing the actual references. There are just too many of them. The Japanese paper, I think, has got something like 500 references. So it's a lot of work to read and to write. Now, let me say something about the dynamical limits. Again, the green regions are excluded. If you've got neutron stars and white dwarfs on the left, these will capture the primordial black holes. And then the primordial black hole, having been captured, may then swallow the neutron star and the white dwarf. So the neutron stars will disappear. You know, it's rather like one of those Jaws movies where the shark swallows something and then it swallows a bomb and the bomb explodes. It's a little bit like that. The neutron star is like the shark which is swallowing the bomb, which is the primordial black hole. But it's not exploding, of course. It's just the black hole is just swallowing up the neutron star. But again, these limits are shown with dotted lines because we no longer believe them. But it's still very interesting historically. And of course, even if we don't believe them, that means there still is an effect. It's just not as big as we see here. Supernovae, this is at low mass also. Remember, these are going from 10 to the minus 15 to 10 to the minus 8 solar masses. So again, sort of asteroid mass range. The idea here is that when a primordial black hole goes through a white dwarf, it can actually trigger a supernova. It makes a shock wave which triggers a supernova. So that's quite dramatic. But again, it's an interesting effect, but the limits probably aren't correct. We now come to the more secure limits. Wide binaries. The idea here is that in our galaxy, we've got these binaries which are very widely separated, which means they're only weakly held together. And if a primordial black hole goes nearby, its tidal field will separate the components. And so binaries, wide binaries, disappear. And the fact that they still are around gives us this constraint, which goes from 100 to 110 million solar masses, which is shown up there. I'm not going to explain the precise form of the constraint. It sort of falls down and then flattens off. But that's described in the notes.
Can I ask a question about the supernova?
Yes, of course.
Thank you. So is what's happening here that the primordial black hole is emitting Hawking radiation, the Hawking radiation causes the explosion, or is it that there's like a physical disturbance in the way?
Yes, I thank you for this. This is all of these black holes are much bigger than would be exploding by Hawking evaporation. You'll notice the mass begins, if you look at the lower axis, it begins at 10 to the 15 grams. So none of these black holes are subject to Hawking radiation. So when I talk about an explosion, the black hole causing a supernova explosion, it's not the Hawking explosion. The black hole, in passing through the white dwarf, generates a shock wave which initiates nuclear reactions, which causes it to explode. Okay. Now, globular clusters, it's rather like the idea with the binaries, only a globular cluster is a gravitationally bound group of stars. If a black hole goes past, its tidal effect will tend to disperse the globular cluster. In fact, what happens is every time it goes past, it sort of expands the cluster, and eventually it may disperse it altogether. And so the fact that globular clusters still exist gives us a limit, and that's in the range 10 to the 4th to 10 to the 10th solar masses. So this is this little line here, down here. So we're getting now into large masses, you notice, the mass range which would also apply to non-primordial black holes. An equivalent effect is associated with it's called Aug13. It's a dwarf galaxy, and at the center of this is a star cluster. And if the dark matter in the dwarf galaxy was primordial black holes in a certain mass range, it would disrupt the star cluster. And since it hasn't, that puts constraints on objects in the mass range 100 to 1 million. So that's this line here. Okay. Now, disk heating, we're going up, notice now in mass. The idea is if the halo of the black hole, our halo was, for example, black holes of 1 million solar masses, it would heat the stars in the disk, and the disk would puff up, and that isn't observed. So that gives an important constraint on black holes in the range 1 million to 1 billion solar masses. So there is the disk heating limit. Dynamical friction, if you've got big black holes in the halo of a galaxy, the dynamical friction of the normal halo stars will drag them into the core, and then you would get too much of a buildup of black holes in the middle of the galaxy. We know there's a 4 million solar mass black hole there, but it can't be more than that. And that gives us the constraint here, which really goes all the way from 10 to the 4th, all the way to 10 to the 12th solar masses. You might ask, why do all these constraints have this diagonal line here? They all, at the right-hand side, they all look like that. That actually corresponds to having one object per galaxy. It's what myself and Florian call the incredulity limit. So it's not strictly a dynamic, it is a dynamical limit, but it's from the requirement if f is so large that you would have less than one of these objects in the halo, obviously the limit doesn't make sense. Now finally, you go to even bigger black holes. If you look in clusters of dark matter, we know clusters of galaxies have got dark matter. If there were giant black holes of galactic size in clusters, they would induce tidal distortions in the visible galaxies, and that's not observed. And so that's the constraint shown up here, which goes from 10 to the 10th to 10 to the 15 solar masses. And finally, on the biggest scale of all, you have what's called the CMB dipole anisotropy. If there were really enormously large black holes in the mass range above 10 to the 18 solar masses, The nearest one, it's a long way away, but it would induce a peculiar velocity simply through its gravitational Coulomb field. And that would induce a dipole moment relative to the microwave background, the CMB. And the fact there's a strict upper limit on the CMB dipole puts a constraint, and that's shown by the diagram on the right here. And so that actually shows there is the cosmological incredulity limit. This actually shows the biggest black hole you could have in principle is about 10 to the 21 solar masses. And you'll notice there is this window here where there are no constraints. This is what we call the stupendously large black hole, the slab range. And it's, as I said, we're not proposing that dark matter's there, but there's nothing in principle to stop there being black holes there. Now, I'm not. There are other constraints which go into the Japanese diagram. I'm not going to talk about them again. I'm just going to give you an impressionistic view, just so you know they do exist. There is the evaporation constraints. We're not really interested in the evaporation constraints because we're only interested in the dark matter. But I'm just showing that. And then there are also constraints associated with accretion and indeed the gravitational waves. But again, I would refer you to our notes if you want to read more about those constraints in detail. As I said, there are a huge number of references here which we're not showing. Now, I want to say a little bit about evaporation constraints though, because at the moment, I said they're not really relevant to the dark matter problem, but you'll remember in an earlier lecture, I showed this constraint here, which goes back way to 1994. It was a constraint on beta as a function of m. And I just want to show another picture, which is again enormously complicated from the Japanese paper. Don't take in this information. So especially the lady who asked the question, please don't get overwhelmed with this diagram. The point of this diagram is, as I said, impressionistic. I just want to convey there are lots of constraints, and it represents a lot of work, and by many people. So notice the mass range goes all the way from 10 to the 9th to 10 to the 17 grams. But because we're only interested in black holes bigger than 10 to the 15, the ones that don't evaporate, I'm going to immediately, this is 2021, just to show, you see, basically these are the same constraints, so it's in the evaporating range. I'm just trying to show you how they've evolved in 17 years. But I'm immediately going to hide all the ones there because they're not relevant to you. You're interested in dark matter. But the ones on the right are relevant because these are black holes which are still evaporating, but they haven't completed their evaporation. And those black holes are still important. They could in principle still be providing the dark matter because they haven't evaporated. So they can produce the gamma ray background, cosmic rays, and there are a host of papers on these topics. Now, I'm not going to show, but the point is, what's being constrained here is beta, by the way, not F. You remember F and beta are simply related. This is a constraint on the collapse fraction. The other previous diagram was the constraint on F. However, I've decided not to show any specific paper on constraints because there's just not time to do it. I'm going to make one exception, however, and I want to cite an important paper on evaporations which came from Mathieu and Boudot and also Marco Cirelli. Now, I'm doing this for two reasons. One, of course, because Marco is in charge, and I just want to stress he himself has made an important contribution to this subject. And thank you, Marco, for inviting myself and Florian to talk. But actually, the other reason is a sad reason. I don't know how many of you knew Mathieu Boudot. He worked with Marco for 3 years, and he was very young, and he wrote this particular paper. And sadly, he died, I think, in January 2020, just somewhat over a year ago. And it's a sad loss for the field. So I just wanted to have a moment's pause just to remember Mathieu. And I should also say, the last paper I wrote with Florian, which was only a few months ago, just before our paper appeared on the archive, and Mathieu was the first author, and so he beat us to it by 1 day. And so even though he'd already died by then, he's still making a contribution. So really, this is just a small tribute to Mathieu. Anyway, what this diagram is about, it was just showing how Voyager 1 observations have measured the positron flux, and that you would expect black holes bigger than 10 to the 15 solar masses to generate positrons. And so you get constraints on the fraction of black holes in that mass range from the Voyager 1 observations. So this is the only specific paper I'm going to talk. Sorry, a comment?
Yeah, I have a quick question.
Okay.
Just saw all these plots in fraction of dark matter. Just to be clear, these are somewhat synonymous with the exclusion limits on the existence of primordial black holes in general in certain mass ranges, right?
Yes. Sorry, who is that talking? I don't know who was saying that, but I just... Sorry?
Hello.
Anyway, not to worry. I wasn't sure if it was Marco himself talking, that's all. Anyway, let me carry on. Another final really complicated, you're probably getting completely overwhelmed with these diagrams, but to be honest, I see them more as works of art because they're really rather beautiful. This is the constraint on beta as a function of mass. This time, again taken from the Japanese paper, this time it goes all the way from the Planck mass to 10 to the 55 solar masses. And this combines all the constraints which come from the Japanese paper, you know, on the non-evaporating black holes. The paper from the Japanese was non-evaporating ones, and then I showed the evaporating constraints. So in some sense, although this diagram is horrendously complicated, it's also horrendously beautiful because it has all the constraints on beta in one picture. And remember, the key point about this, a point I made right at the beginning, was that only a tiny fraction of the universe can have gone into primordial black holes, and that was the fine-tuning problem. You only expect a tiny fraction of the universe to collapse in most scenarios, but only a small fraction can have collapsed. Okay, so, and then just to say that once you have these constraints, you also get constraints on the power spectrum of the fluctuations. I know you've heard quite a lot about the power spectrum from Anne Green and from Florian, and this is a diagram that Florian showed, showing how you go from beta to constraints, the constraints on beta to the constraint on epsilon, the horizon fluctuations, which is equivalent to the power spectrum. I thought again you might be interested in how you can go from the constraints from the Japanese paper on the fraction of dark mass. Remember, this is beta, this is f, but they're simply related by an m to the half factor. If you look at the constraints on the power spectrum, again, this is epsilon, which is the horizon amplitude fluctuation. This is the power spectrum as a function of k. So this upper right diagram is equivalent to the upper left, lower right diagram. It's just this is epsilon as a function of m, this is the power spectrum as a function of k. But the point is that these are equivalent diagrams, and again I just think this is a rather beautiful diagram because you're using the same color coding. So anyway, I realize all these diagrams have got a huge amount of information, and there's far more information you can take in now, but if you want more details, you can, of course, read the notes, which I'm sure you have already read all the notes, which myself and Florian circulated. And indeed, you can read the original Japanese paper if you want even more details. Okay, now, I want to make some comments, though, because you're probably getting a little bit worried about all of these constraints. And you might say, well, if myself and Florian, if we're so determined to spend our lives working on primordial black holes. I mean, I've worked on them for 50 years. Florian is much younger than me, but even Florian has worked on them for probably 10 years. And the question is, why, you might say, are we focusing on all these constraints? Because on the face of it, these constraints are nails in the coffin of the primordial black hole scenario. And so what I want to stress is you should not regard these as nails in a coffin. First of all these constraints have caveats. I think Florian showed in one of his slides yesterday that actually many of the constraints have gone away. Of the constraints we showed in our 2016 paper, several have gone away. And you remember some of the constraints I showed in my diagram of the Japanese work had dotted lines, meaning there were uncertainties. So all the constraints have got error bars. They may be uncertainties associated with the theory, or they may be uncertainties associated with the observations themselves. Sometimes the observations go away, sometimes the observation stays, but the theory turns out to have a mistake. And of course, all of the constraints change with time. I mean, obviously, a lot of the constraints, such as the LIGO observations and some of the microlensing observations, we've only had for a few years. But the other point I wanted just to stress this, the next slide, one of the biggest uncertainties, I mean, for example, you looking naively at the Japanese, when I say the Japanese, I mean that paper I did with the Japanese, you might infer you can't have the dark matter at around a solar mass because the limits seem to exclude F equals 1. However, there's a really important caveat which I want to stress here. All of those lensing observations assume that the black holes aren't clustered. They assume they're uniformly distributed. But actually, if the black holes are clustered, strongly clustered within the halo, I mean, obviously they're clustered in the halo, but even within the halo, if they're in subclumps, then the constraints can be very much weakened. Because, for example, if you had million solar mass clumps and 1 solar mass PBHs, there would be a high chance that you wouldn't be having one of these clumps in front of a star anyway. So all the constraints depend upon this. And if, for example, you have a log normal mass function, which I think Florian argued for yesterday, the constraints are all changed. And so this is the idea is that in many inflationary scenarios, this actually happens. So you might expect you're going to get a uniform distribution in the halo, but actually you get clumps like this. And that change, and I've just cited one paper by our collaborator, Juan Garcia Bellido et al., which looks at this problem. So this is actually the viability of black holes as one solar mass dark matter candidate crucially depends on whether they're clustered. Now, let me carry on. The other point sorry, a question?
Yes, thank you. So with these log normal PBH mass functions, would the bubble nucleation scenario lead to that kind of log normal mass function?
Yes, well, now that's quite an interesting question. Let me just go, I don't know, can I go back? I'm not, oddly enough, I don't think I can go back with this for some reason. Yes, I mean, in the clustering picture I showed, the black holes themselves have a range of masses. They have a log normal mass function. And so there is a link between whether the PBHs have got a mass function, an extended mass function, and whether they are clumped. So the two issues do go together. But I'm coming on to the mass function later, so let me postpone the question, that answer to that question a little bit. Now, the other point I want to say is that even if primordial black holes have much less than the dark matter density, they can still be enormously interesting. I mean, there are many interesting problems in astronomy besides the dark matter problem. I mean, for example, you could argue the most important component of the universe is human beings, at least on this planet. But the mass of human beings, their contribution to the dark energy density is completely negligible. And this is true in particle physics as well. For example, nobody believes that neutrinos explain the dark matter anymore. At one stage, they were a candidate for the dark matter. But we now know they don't make the dark matter, but we also know that neutrinos are incredibly important. And there are all sorts of experiments people spend their lives doing with them. And it's like that with primordial black holes. Even if primordial black holes don't explain the dark matter, they can do all sorts of other interesting things. They can, for example, provide the seed for the supermassive black holes in the centers of galaxies. And we're going to come on in Florian's talk to discuss other things primordial black holes can do, even if they don't have the dark matter density. The other thing is that every constraint is a potential signature. And whenever I talk about a constraint, the original hope was that that constraint, be it lensing or dynamical effect, might be a signature for black holes. And indeed, historically, many of these constraints have been interpreted as signatures. Let me just give you a very simple example about dark matter. I've talked about microlensing of dark matter in the LMC or the M31. So the idea is, here's a picture. You're looking at a star in the LMC, and if a black hole in the halo gets in the way, then you see a variation in the luminosity, which is an indication of the presence of the dark matter. Now, when this experiment was first done, which was in the 1990s, at first they found evidence. I mean, there's going to be some lensing anyway through ordinary stars, but they found an excess of events. And these suggested that, in fact, the dark matter was what they called machos in those days, a more generic term than primordial black hole, massive compact halo objects, with a mass of about 0.5 solar masses. Now, that was tremendously exciting because at that stage, people thought it would be quite natural for the black holes, the primordial black holes, to be formed at the QCD phase transition, in which case they would naturally have this mass. And so people like me were really excited. This was way back in 97, I think, because we thought, now at last we have the evidence that primordial black holes exist. And also we expected black holes to form because, as Florian's going to talk about and has already mentioned, you do expect the pressure to go down at the QCD phase transition. So we also expected primordial black holes perhaps to form then. Later, however, just a few years later, we found that the dark mass in this object could only be 20% of the dark matter density. So that was a bit of a blow, bit of a disappointment. Here is a more precise, this is the lensing constraint. This is the fraction of mass, what I was calling F as a function of mass. I've already shown this constraint as part of the master constraints diagram, but it might be interesting to show it here. Here is the macho observation, which actually was a positive detection, remember. We still don't know what those events are. And here were the Eros constraints, this region here being excluded. And in particular, you see you can only have about 20%. However, I do want to, so at that point, people said, oh, well, it can't be primordial black holes after all. But I do want to remind you that this all assumes there is no clumping of the dark matter. And actually, later on, Florian's going to talk about a scenario where we do want the dark matter to be in these black holes. And we get round the constraints precisely because they got an extended mass function and there is clumping. And I should also mention another historical result. Mike Hawkins, who's still active, in '93, he was looking at evidence for the microlensing of quasars. So you have a long time scale variation in the quasar luminosity, which he said could be associated with primordial black holes. They're at a cosmological distance, so the time scale is much longer. And he even wrote a book on this in 1993. And I have to say, at the time, astronomers weren't very convinced by this, but I think now there's more evidence for this. And the only thing is he's now changed his favoured mass from 0.1 to 1 solar mass. So again, this is historical evidence, which I would have represented by a dotted line. I mean, this was not being used as a constraint. It was being claimed as positive evidence. Wherever you have evidence, you can also interpret it as a constraint. So, but then the other point I want to make, which just relates to this question, is that generically primordial black holes will have an extended mass function. And all the constraints change if you have an extended mass function. Now, I have to say, this is a slightly complicated discussion, but let me just say, myself and Florian wrote a paper about this in 2016. The question is, can you evade the limits by having an extended mass function? When I say limits, I mean those constraints on FM in the complicated color diagrams. And actually, this is it's a two-edged sword in the following sense. First of all, you might think primordial black holes could be dark even if they have a low fraction of mass at any particular scale. I mean, if your black hole are spread over a huge mass range, they could make up the dark matter even if their density in any particular one is low. So you might think that's good news. On the other hand, another problem is that if you have an extended mass scale, that could mean that even if the black holes have the dark matter density, you know, in a range which is allowed, it may be with an extended mass function that they're going to violate the constraints at some other mass range, either lower or larger. So it's not completely obvious certainly when myself and Florian wrote our paper about this, it wasn't completely obvious whether this helped. And now we have a much more precise analysis, which is, this is a little bit technical, but you have to first of all describe what a mass function, and we do that by introducing a function psi as a function of m, which when integrated, of course, just gives you omega pbh. So it is essentially, it's the mass, it's m dn by dm. And you will have heard about various mass functions. There's the log normal mass function, which has been talked about. Often you get a power law mass function, for example, if the black holes form from cosmic strings. And Florian's also talked about critical collapse. So these are probably the three most likely mass functions, which you've heard about. And in each of these cases, you have to do the analysis. Now, the way you do the analysis is a little bit complicated. What you have to do is, you take the constraints if you have a monochromatic mass function. And the way you do it is your constraint, you have an integral of the constraint, which depends on Fm max. And then you have to feed in the fact that you have an expected mass function, which depends upon the Fpbh, the dark matter fraction. It depends on some characteristic mass, which I'm calling mc. For example, that appears in the log normal mass function. And it depends on sigma, which is the width, the dispersion of the mass function. In all of these cases, you effectively have two parameters. And then what happens is you get a constraint on f as a function of mc and sigma. And this is some work which I did with some collaborators in 2017. I mean, that's an old paper. I'm sorry, I'm referring quite a lot to my own papers here, but they're the only ones I understand. Now, the important point is, this is the constraint which you saw before from the Japanese paper. You can't just plot the mass function, because that doesn't work. The constraints themselves change. So the FBM constraints themselves change. I'm just showing what happens in the log normal case. And so the constraints change, and then when you do that, you get a limit. This is plotting sigma against m, and the value of Fm of F max is given by the color here. So for example, this dotted white line corresponds to F equals 1. So you see the analysis is much more complicated. By and large, and I'd refer you to our notes if you want a bigger discussion of it. It's quite complicated, this, but by and large, the answer is it doesn't help much. So that's probably the bottom line, but you will need to read the analysis to understand this more carefully. Now, some final points. Sorry, this is my final points in the next lecture. So I have now finished. I've taken 45 minutes. I'm going to stop sharing now. If anybody, stop sharing my screen, unless anyone has some points they would like to make, questions, we can go straight into Florian. Are you ready, Florian?
I am, yes.
So unless there are any final questions, I hand the floor over to Florian.
One
here, one short, one.
So I have a kind of general philosophical question. Why do we say primordial black holes don't require new physics, while at the same time we know they cannot be baryonic because they form before Big Bang? I would say they're not baryonic, they somehow require new physics.
Well, that's interesting. I said in my introductory lecture that black holes definitely exist. And so I said, in that sense, we don't need any new physics. But it is true, of course, that when you're making primordial black holes, you are depending on new physics. Now, it depends what you mean by new physics. If the black holes are forming from inhomogeneities, which in some sense is the most natural scenario, inflationary, inhomogeneities. In that sense, you're not using new physics. On the other hand, you might say inflation is new physics, because inflation requires you have some inflaton field, for example, and so that is new physics. If the primordial black holes form from cosmic strings, you're invoking the formation of cosmic strings, so that's new physics as well. And in fact, every scenario, in fact, I would say the scenario which doesn't require new physics is the one that Florian is going to talk about, which is to do with QCD phase transitions, because we do have information on what the QCD phase transition will be like from accelerator experiments. So your question, when I made the argument before that PBHs don't depend on new physics, whereas particle physics, dark matter does, you're right, that's oversimplistic, because many of the primordial black hole scenarios do depend on physics which is still untested. At the end of the day, anything one says about the early universe before about a second, well, before the QCD epoch, is speculative and is new physics. So that's a good point, thank you. And now I think I'll hand over to Florian if he's ready.
Yes, I am. Right, thanks.
He's going to talk about established physics.
Let's get it there. Hello, microphone works. Fantastic. So, hello everybody. So it's my pleasure to sort of come to this part, which is probably my favorite part, not just because together with Bernard, I authored that paper where we describe the scenario, but also it's a very beautiful, we argue, very natural scenario. And about these 2 points, I hope I will be convincing. So let me start. But before I go actually to primordial black holes, let us step a little bit back and look how the thermal history of the universe affects, say, the number of relativistic particles. So here I put the effective number of relativistic degrees of freedom, and that is a function of temperature. Yes.
Yeah, hope it's right.
Okay.
Go ahead. Don't
Okay,
worry.
no, can you go? Let's see, step on back. So, I can't change.
Oh, sorry.
Yeah, yes. So here we have the temperature and MEV, and here we have the number of effective number of relativistic degrees of freedom. So actually time goes from the right of the diagram to the left of the diagram. Now, what happens when time evolves? The universe cools down. So at the beginning, sort of, basically all the standard model particles are sort of relativistic, and then the universe cools down. More and more particles become non-relativistic, sort of top quark, the WT boson, and all the way down there's pions and there's some electrons. So you see that there's an evolution and a decline of the relativistic degrees of freedom. But what is the main importance of this for our talk is that this actually has an effect on the effective equation of state parameters. So in the earlier slide, we call this alpha and later W. So W is P over rho, so it's the proportional constant between the pressure and the energy density. And if you had radiation, you would be up at this mark. So this is just 1/3 on this scale here, this W. And this is again the same x-axis showing the temperature as it cools down. And whenever you have a drastic change of the effective degrees of freedom, you have a change in this equation of state parameter. Now, if you remember what I told you, I think in the last 2 lectures and different times, is that whenever you change the equation of state parameter, you actually change the threshold for primordial black hole formation. So in particular, this goes hand in hand with the reduction of pressures. You have several dips where actually the pressure, which makes it difficult to form black holes. So you have 2 competing forces. You have basically the pressure that is working against the gravitational attraction. And so, and this, when the pressure is lowered, like it is the case in the around the QCD phase transition, which is around here, you would have sort of preferred conditions for forming black holes, and that would lead to a larger amount of black holes. And let me just stress one fact, is that the dependence of the abundance of produced primordial black holes on this equation of state parameter is exponential. So you have, even though you have only a dip of, say, 10%, or a little bit more, but around 10%, you would change the abundance or the dark matter fraction of primordial black holes by orders of magnitude. And how does it look? So I can't change the slide. Yeah, so that would look, sorry for the technical problem. So that's from a paper which Bernard mentioned already, which we worked together on with Sebastian Klass and Juan Lucia Bellido. This shows basically, this is a scenario in which you have basically almost scale invariant fluctuation. We have basically a featureless power spectrum, which has a little tilt. And then what the thermal history of the universe does for you is that, when I go back again, no, it's strange that I can't change. Anyway, you remember the diagram from before, where around the QCD phase transition, you had a dip in the equation of state parameter, and that dip was about 10%. And then you can see how sort of that gives a boost around a solar mass. Then you get another a bump that is related to the Lecture2 transition, which enhances the production of primordial black holes around here. And then you have the plus minus annihilation, which happens later, and later means a bigger horizon mass, and that means you sort of produce larger black holes. Okay, and with this diagram, actually the integrated dark matter fraction is the total amount of dark matter is 100%, and we will show you what is really beautiful about this is that you can solve several observational conundrums. First of all, the most important thing is that you can account for all the dark matter, and then you can account for several instances. Of course, this diagram again is complicated, and one important fact is because you see several different lines in here, and these lines correspond to different spectral indices. So it's the spectrum, the power spectrum has simple power law form. So k to some power, and this power is a spectral index. And this spectral index, it's not important, and a priori it has nothing to do with the spectral index from measurements of Planck, but it turns out, as a coincidence, only for values of the spectral index in a narrow range around the one which you measured from Planck, which Planck measured, and also WMAP, which is 0.97, then you avoid sort of, I need to click here. Yeah, so then you avoid either overproduction of light black holes, because then you see that this curve changes here, the green curve goes up here. So you have these small black holes that are overproduced and then would violate constraints. And also you would have an overproduction of large black holes if the spectral index is too small. That means, we know pretty precisely how much of these very heavy black holes we could have. And with this sort of magic number of 0.97, we could have exactly the right amount to explain several observational conundra, which I'm now going to go into. Now, so the thing is that Bernard already mentioned this microlensing observation and overlay. I think it's a Polish experiment, and so they detected several microlensing events. They have a big population which they understand very well of long lensing time scales. So this is microlensing as opposed to strong lensing. So microlensing is just if you have a lens at the source, and the the black hole passes in front of the source, it changes the luminosity. And when I say time scale, I mean the time scale that light curve varies. Okay, and they have a population which you understand very well. Actually, the curve would continue in here, and now, but they also have a population of like short time scale events. This is time scale of hours, and the others are days to almost a year. So this is time scale of hours, and if you look for an explanation of this, then the standard repertoire, and let's not put primordial black holes yet in the standard repertoire, then the best explanation they could come up is with free floating planets. But actually, the amount of dark matter which you would need, or the amount of the free floating planets which you would need to explain this would be a few percent of all the dark matter. So that is, in most scenarios, far too many of the free floating planets. So they actually, in this paper, even though they were not coming from the primordial black hole side, they were entertaining the possibility that these 6 events which we measured are originating from primordial black holes around Earth mass. Yeah. So here we have the diagram. So here it's a dark matter fraction of primordial black holes as a function of mass, and here's sort of one excluded region. This gray region is excluded by this AGC experiment that Bernard mentioned, and they said it can very well be in this range. So it's a few percent of the dark matter, which could be of primordial black holes, and which could explain this. And actually, in the scenario that I showed you before, that sort of the different curves which you've seen before, is our theoretical prediction for the primordial black hole mass function. This magic choice of this spectral index of 0.97 actually yields a few percent of the dark matter in primordial black holes in the planetary mass range. Okay, so this is one of the bumps we went through. And there are a number of different other microlensing observations. I won't talk too much in depth about these, but there's also microlensing observations, which let me just click here. Yes. Well, there's this also quasi microlensing events that sort of we didn't have really a good explanation for in our standard repertoire, but primordial black holes could do this. The same with sort of excess of galactic lenses in the galactic bulge that could also be explained by our mass function. Then, even so, I mean, I'm now going a bit quick. We can talk later on a bit more in depth, because there's before the break there's quite a bit more yet to come. So there's of course more in the notes, and we can discuss this more details later on. But there's also a little bit, not a little bit. There's also some correlation, a strong correlation between the cosmic infrared and the X-ray background. And these could also be produced in exactly the same way that is observed by primordial black holes. Then there is another thing, sorry for going a little bit quick through this. There is also, so when you have these, when I mentioned the Eridanus 2, and this is an ultra-faint dwarf galaxy, and ultra-faint dwarf galaxies actually are not observed below a certain radius, and primordial black holes could be a reason why these objects are actually unstable, why they are dissolved. Now, after going a bit quick through these conundra, let me elaborate a bit more in detail about probably one of these.
Florian, you got plenty of time, Florian, so you don't have to rush.
Yeah. Well, let me come back to the other conundra later. Let me explain this, and let's see how much time we have later. So. Okay, so, and one of the major predictions of our model, and where of actually the biggest peak is that we see here's again our mass function, of the prediction for the primordial black hole dark matter fraction. You see that this is actually here with this big peak and this what's called the time plateau. They are in a very sort of interesting range, which is in the range which LIGO and Virgo and probably Keckra can access. Now, before, so the first version, the archive version of our paper, that when it came out, there were now no O3 events. And so we made a prediction of this is here, and on this diagram we have the masses of the two merging black holes that sort of could merge, and the detection likelihood is given here with a color coding. So the brighter the color is, the more likely is the detection. And so we predicted sort of basically three regions where you should be able to detect, or in the future we should see mergers detected with LIGO if our model is right. Now, and so in the process when we were publishing and going through a review process of our paper, in the meantime, actually three events, LIGO events appeared, and this is sort of one event. One event which is actually at very low masses. One has a very low mass ratios because we predict also unequal mass ratio. It's basically, so you have this big peak around the solar mass, a peak around a bit more than 10 solar masses. So if these order 10 solar masses, so if these two sort of merge, you should get this low mass ratio merges. And of course, you see that our distribution extends to larger masses. So that would actually lead to very heavy black holes. And so now people, or some researchers, which sort of looked at how heavy black holes can be from at the end product of stellar evolution. At the beginning was thought, well, probably so 80 or even 60 solar masses only are the maximum. And now they're revising models and they come up with sort of prediction for even around 80 solar masses, but we predict actually masses in this mass range. We don't need to change any stellar evolution model. And we actually our scenario predict even a large population in this range. So here we should see in the future, hopefully with O3b or the O4 run of LIGO, we should see many more mergers, and also like the small ones. And probably the biggest, I would say probably the most smoky of the smoking guns is would be the black holes sort of in the very low mass range, in particular those that sort of reach even below a solar mass, because that is certainly not a product of stellar evolution. But even a solar mass is difficult to produce. And usually in this mass range, you would look for neutron stars. So probably above 5-ish solar masses, you would only think, or traditionally would only think this is black holes. But the primordial black holes, of course, they are not subject to this mass gap. They could fill all the mass gap, and we predict that they should actually fill this mass gap, and we should see a larger population also in this mass range. Now, of course, above this mass gap, say above the 5-ish solar masses, these black holes could have been a result of stellar evolution. And then the question is there a way to discriminate, or at least a way to be more convinced that these could be of primordial origin? And one interesting prediction for primordial black holes, at least in our scenario and in many scenarios, not for all scenarios, but for a large class of scenarios, including ours, this is extended mass function with the different bumps, is that basically the expected spin which these objects have should be rather low. So there's a nice theoretical work by Shibata and Yokoyama who predicted the spin distribution. So A is a spin parameter, so A equal 1 means maximal spinning, basically. And so here you see that this is peaked around 0. So primordial black holes basically shouldn't spin in most scenarios, I have to say. Of course, there are other scenarios, but in our scenarios, they shouldn't really spin much. And when you look at the effective spin parameters, this chi-f, so chi-f is basically a weighted projection of the individual spins. So the individual spins are called S. So S, say Sj, for J being 1 or 2 for the two merging masses. So you have the spin over the masses, so S1 over S2 plus so time scalar product with 2/m2, and this is projected onto the total angular momentum. Now, and of course, there's different ways to produce this effective spin parameter, also to arrange in a particular way to 0, but this you wouldn't expect really. But what is measured, what has been measured with LIGO, is for a number of events. I think now we would have even more. This is a longer list of the measured value for the effective spin parameter, which is basically as either consistent with 0 or with very little spin. You see, and you see it's large error bars, yes, because it's easy or relatively easy to say what the final spin is, but it's a bit more complicated to deduce from the observation the individual spins. That's why the error bars are quite large. But you really notice that most of them are centered around 0 or are not very far away from 0. So of course, this is not a proof for that these black holes that we measured, these mergers that LIGO measured, are of primordial nature, but they are actually in this is in line. See a question over there? Please.
I was just wondering, so why are the spins expected to be low? What is the reason, the physical reason for that?
So, this is this scenario which we discussed, yeah, or which I showed you with these different bumps. It's also a scenario which sort of originates from there's different sort of very basic scenarios you can write down, but essentially this is inflationary perturbations, and you have this large overdensity, sort of that at some point fits into the horizon. You have something which is sort of, you start non-spinning, and then you have a gravitational collapse to a black hole. So at some point, these overdensities can come in causal contact and can undergo a collapse process, and they start basically non-spinning. And of course, you may have small perturbations, and also on the way, it's like the ice skate. When you have tiny perturbation, it can speed up a little bit, but actually you would not expect to have a large spin by these processes. You start with something very big, non-spinning. So at the beginning, it doesn't the initial overdensity is collapsing. So something that is irrotational, and then sort of you get a collapse from there. I mean, sorry, if you want to trace
Florian, could I just interject just to explain it again? The point is, these overdense regions, they come in the horizon, they stop expanding, and they don't collapse much before forming black holes. They have to be close to the horizon size, so they don't have to collapse very much at all before forming a black hole. Whereas the black hole which forms from stellar collapse, it starts from you have a cloud which is collapsing an enormous amount, so it spins up. So that's the reason why the primordial black holes don't have spin, whereas the stars do. Sorry, Florian, over to you again.
Okay.
Okay, thanks.
All right. So this is something that, like I said, this is sort of indication that tells you we are not totally off. Of course, if this KF would be telling you that the individual spins were really, really large, and probably that would speak against our scenario. But so far we are sort of a little bit back up by this observation. Now, if you go to the larger side of the different bumps, we have this mass spectrum actually in this sort of around 10 to the 5 to the 6 solar mass range, or even in a range around these masses. You have black holes that are actually very good seeds for the supermassive black holes in galactic centers. I mean, so it's a question in astrophysics also how to produce, like, for instance, from stellar collapse, from a star that has probably 50 solar masses or even 100 solar masses that collapses to a black hole, how to produce, or how to then end up with a black hole of 1 million, 1 billion, or 10 billion solar masses. So you have, of course, you will have growth, but it's still a bit challenging to go to these enormous masses. And of course, these primordial black holes, which are already quite heavy, say it's 100,000, 1 million solar masses from the start, they would be providing quite a there would be quite good seeds for these supermassive black holes in galactic centers. And actually, when you when you look at a relation between the observed sort of the black hole, the mass of a black hole, which is shown here, and the mass of sort of the galaxy which they're sitting in, then there's sort of a relation of the different population that we see. And actually, our model can also sort of explain this relation between these, the mass of the black hole and sort of the galaxy which is hosted. Now, let me go to actually probably the topic which sort of, brings together the discussion on primordial black holes and probably the research activity of most attendants of the, or most participants of this school. And basically, so Bernard showed you, and me too, we showed you a lot of constraints on primordial black holes. And you may ask, okay, what if primordial black holes do not form the entirety of the dark matter? What is the rest? I mean, inevitably, if primordial black holes are part of the dark matter, but not providing all of it, there must be something else. And of course, what the something else is a question you may ask. And one sort of reasonable assumption you can do is sort of you have a combined dark matter scenario consisting of primordial black holes and particles. So when you have, and these particles, of course, they could be WIMPs, but whenever you have such a scenario, what would happen since the primordial black holes are around for a very long time, and you have sort of there an environment of other dark matter particles, these other dark matter particles would be gravitational bound and build up a halo around these primordial black holes. And so actually what is then a good way to constrain these scenarios, to probably look for these scenarios, is to look for sort of annihilation signatures. I mean, the point is that the annihilation rate, WIMP scales like the square of the number density. That means if you have a halo, so you have probably more or less uniform WIMP distribution, or at least not as large overdensity as you have around these primordial black holes, you can have to get pretty strong density spikes, and we'll show you later sort of how these spikes look. And we made a simulation to see really how the profile is. But then you would have the large enhancement of the annihilation rate. So this is the physics for detecting this. And actually what sort of, there's the program, so what we did. So first of all, many people did, it's not us, and it dates back several years, where people calculated the density profile of the WIMPs captured by the primordial black holes. Then you can calculate once you know this, you can calculate the annihilation rate. And of course, then you can compare these signatures to what is observed. So by Fermi, what's observed in terms of the electric, the extragalactic gamma ray background. And so the first step in this list was to come up with a profile. It's now complicated diagrams. Again, probably it's not as complicated as these big master constraint diagrams, but still it's a bit cluttered. So also, don't try to grasp everything immediately. So here we have the dark matter density around the primordial black holes as a function of radius. And there's two types of lines, basically. So let's focus just on one color. So let's see the different. This is here for this green line is for this lower line. These three lower lines are for say black holes of 10 to minus 12 solar masses. So this is actually very light black holes, and you can have sort of Earth mass black holes, and then you have black holes of solar mass and 10 and a million mass black holes. But so the different line types in terms of solid and dashed mean that the solid lines are sort of the sort of what is initial or older profiles, and the dashed line are the profiles that you would have today. And you see a stark difference here, and in particular see a plateau. And the plateau comes from annihilation. So over the course of time, if the energy, the density of these dark matter particles, the WIMP particles, is large enough, they would annihilate. So they would just shrink these densities to get actually a plateau. So each of these modes at some time will have a plateau, and then a power law fall off. There's a number of, there's different form of each, and there's different stages in length or in distance from the center, where you get different power laws, but let's not go into details, but the main thing is to get a plateau, basically, from WIMP annihilation, and then you get an exponential fall off.
Florian, can I just interrupt?
Please.
If you could show the figure again.
Yes.
I just want to point out that we've cited our own paper there, but I have to say that one day before our paper appeared on the archive, a paper appeared with basically the same profiles as we've got here, and that was the paper by Matthew Badoud and his colleagues. And so we were very well. They actually beat us to these profiles by one day, and we worked on this problem for 6 months and found it very hard. So that what I think is probably the last paper by Mathieu was really impressive, and it came in just before us. So I just wanted to mention that as a tribute to Mathieu. Over to you again.
Yeah. So with the situation where you're looking at these density profiles and the annihilation leads to this more polar profile today, why is this unique to having community like this?
Well, I mean, we need some sort of, the WIMPs are sort of captured by some massive object. In order to capture these WIMPs, you need something that gravitationally attracts them. Of course, if you have some from another theory, some other probably exotic macroscopic candidate or macroscopic body that attracts these WIMPs, you can also build up a halo around them. So in this sense, it's probably not too specific. Of course, if you look very closely, and there's ways to discriminate this, but in principle, you need a very massive body, a compact body in the center, and over time, more and more WIMPs will be captured and build up this halo, and then there's a dynamics to sort of plateau the center.
Okay, so in other situations, you just kind of build up a halo.
You need something which to build up this halo, you need to have some gravitational attraction, and the black holes do this naturally. But of course, if you have, there's other scenarios which have, say, macroscopic bodies of nuclear densities, and there's the paper by Dan Starkman on sort of macroscopic dark matter, which is not primordial black hole. There's another field which is a bit different. There's these, it's called ultra-compact mini-halos. So if you have density fluctuations that are not large enough to form primordial black holes, but yet they could form some very compact structures, and you have also some sort of halo profile. Yes, this is indeed, the formation of halo profiles is not unique to primordial black holes. You have other situations, but of course, when you look very closely to this, and when you study very detailed this sort of the fall off and the signatures, I think you could discriminate some of these scenarios. Okay, so, and that's actually later on, and from comparing the predicted signal, with the predicted annihilation signal to the extragalactic gamma ray background, you can actually draw some, you can draw very tight constraints. So here we have again the primary black hole dark matter fraction as a function of mass, and everything above these lines is sort of excluded. And so here's these very light ones, evaporating ones, or some other constraints which you had before. Here's the impurity limit, which Bernard mentioned, which basically corresponds to 1 in the environment. But let's not talk about these so much. Let's focus on these blue lines. Now, with these blue lines, it's assumed you have sort of standard WIMP of a certain mass, like a TeV, 100 GeV or 10 GeV, and you look for the annihilation rate. Of course, it is depending on the values of the annihilation cross section. I have later on a slide where we actually show sort of when we go through the different parameters, we have a more sort of complete diagram. But already here you see that the abundance, in particular for this not tiny black holes, for these sort of the black holes which are sort of above, say, 10 to minus 6 solar masses or so, you have this plateau, and that is actually tiny. You see the allowed dark matter abundance, dark matter fraction of primordial black holes is, if you have this WIM scenario, this primordial black hole WIM scenario, is tiny. And actually it's so tiny that, so if you then assume, if you go the other way around and say, okay, if the primordial black holes observed by LIGO, if the black holes observed by LIGO are primordial in nature, of course, that would imply that you are not down here. You're probably around, a percent, a per mil, or in that range. You're up here. This would rule out any standard WIM scenario. So this is quite powerful to constrain or to rule out a scenario. I mean, it goes vice versa. I mean, of course, if you one day detected measured WIMs somewhere, you could heavily constrain the primordial black hole fraction. I mean, it goes in both ways, but if you have these combined scenarios, you have super strong constraints. Yes, please.
I say, how many detections do you need? I mean, how many more black holes do you need to detect to actually rule out the WIM scenario? It's just one, or is it
one? I think if you know that this black hole which you detected with LIGO is primordial, since given sort of the detector range, and I mean, of course, it can be super unlucky, but usually if the black holes, a few black holes would be detected with LIGO, if they're of primordial nature, you would have that would imply sort of a dark matter fraction which is significantly above 10 to minus 11. I mean, significantly above. So you don't need many. In principle, if you know that there's one, you would it would basically be enough, because that can only happen realistically if the dark matter fraction is far above these lines.
Or even if not all masses are, when you take one black hole at one mass, it will constrain like one line on the spot. I mean, how do you dispute the fact that there could be other masses for the WIM for this?
Well, I mean, this constraint is for different. Like I said, I have later on a strong constraint, but here, if you have, say, a WIM of whatever 100 GeV, that's the middle line. Yeah, and for any black hole, if you take the middle line from, say, 10 to minus 6 or so till, well, whatever arbitrary large masses, these constraints are so strong as indicated here. I mean, it's, of course, if you change the WIM mass, you go. So if you increase the WIM mass, you go up with these lines. But you have to go up if you want to be ending up somewhere in this range here, where you have just per mil, say, of the black hole, say, which is sort of the range for the LIGO black holes to be the minimal range for the LIGO black holes to be dark matter. Then you would have to crank up the WIM mass quite a bit. I have another plot which clarifies this. So let me just go to this before we go to Bernard's final remarks. So this is now a plot which probably goes more into answering your question, or probably gives a bit more insights in this direction. So here we have the WIM mass as a function in terms of in units of GeV. Here we have the primordial black hole mass, or masses in terms of in units of the solar mass. From 10 to minus 14 to 100, and this the WIM mass goes from 10 GeV to a TeV, and here you see the allowed allowed WIM fraction. And actually here, this is in this model we have that. So if you have the allowed WIM fraction, then this plus for this plot to generate was WIM plus primordial black is equal to 1. So I mean, you can have, of course, a situation. I mean, like I said, to say again, what I really want to say below this, that I mean, for each, there's for small values of FPBH, then we have really heavy constraints on the WIM dark matter fraction. And actually, what we point out, so our paper is called. So I think it's primordial black holes, WIMs, or something else. So actually, all this observation may also point you to yet another dark matter candidate, because you know, if you look at this plot, I mean, for primordial black holes larger than this 10 to minus 11 solar masses and WIMPs smaller than 100 GeV, I mean, both the primordial black hole dark matter fraction as well as the WIMP dark matter fraction can only be 10%. So this, in this case, you're pointed to either abandon this scenario of the standard WIMP because it's sort of can modify this WIMP scenario, or you yet have another dark matter. Yeah. Yes, please.
So I guess on this assume dark matter annihilates through S wave.
Yeah.
It changes a lot if we assume it annihilates through P wave.
It would change the definitely. So I must say I must have to you know, look into this more carefully. But you're right. I mean, this is under this assumption that you mentioned, and if you change from this sort of the standard assumption, you change it. But even if you also look at the annihilation cross section, this assumes a certain annihilation cross section, certain value. If you change this quite a bit, you can make this constraint go away by making the annihilation cross section very, very low. So in this sense, like I said, you have to, if you deviate from sort of the standard assumptions, you change this constraint. By exactly how much, I'm not quite sure. I don't want to say anything wrong. So we can discuss it later together. We can go to the paper and probably do some calculation and have a look how this, in which direction it goes. But the bottom line is the standard WIMP scenarios and primordial black holes are really heavily constrained. So, and with this in the remaining minutes, I think we come back to Bernard. So hand over to you, Bernard.
Thank you, Florian. So if you could, I will share screen. If you could stop sharing the screen.
Yes, let me unshare. Can you do?
Okay, you've unshared.
Yes.
Thank you. So I will share the screen again. So I will, here we go. So I'm on, can everybody see my screen again?
Yes.
I just want to make some final points. Have I got 5 minutes, Marco?
Yeah.
Thank you. So the first point, I just want to come back to a point which I raised in my introductory lecture, which is the fine tuning which is required for PBHs to explain the dark matter. You remember that it's only a tiny fraction of the universe will have gone into primordial black holes, even if they make up the dark mass. And for example, if the black holes form at some time t, we know what their mass is, and we also know what the value of beta is, the collapse fraction, if we know what the dark matter fraction Fm is. And this is just to remind you of the actual relationships, the dependencies on m itself. Now, so beta's fine-tuned. However, we're particularly interested in the situation in which the primordial black holes form at the QCD phase transition. Remember, this was the scenario which Florian described in the last lecture. Now, it's very interesting that one thing you've got to ask is, well, what is the ratio of the PBH density to the baryonic density? Beta stands for baryons. And you remember in the first lecture, I showed that nucleosynthesis tells us what the baryonic density is. It's about 5% of the critical density, whereas the dark matter density is about 25%. So in actual fact, this parameter chi, which is defined by this relationship, is basically 6 times F, where F is the dark matter fraction. So that's a number of order 1. And actually, that is a strange coincidence. Why should primordial black holes have roughly the same density as the baryons? The ratio, more precisely, it's 6. And that's a mystery. That's a deeper level of fine-tuning. We know beta's small, but we need to explain this. But there are sort of reasons why we know it has to be the case that chi isn't too different from 1. If chi was much bigger than 1, that would mean there are lots and lots of primordial black holes. That would mean that the time at which matter dominates the density, what we call T-ec, begins to dominate over radiation, will be much less than the decoupling time, which is when you see the microwave background. And in that case, there wouldn't be enough baryons left to make galaxies. On the other hand, if chi was much less than 1, in other words, if we didn't have the dark matter, sorry, this should be T-ec, not T-dec. T-ec would be much bigger than T-decoupling, and that would mean the fluctuations would be too small to make galaxies, because basically fluctuations can grow in the dark matter between T-ec and D-dec. So if T-ec is after D-dec, that doesn't happen. So you do need dark matter to make galaxies, given the size of the initial fluctuations. Of course, it could still be particle dark matter. But now the point is, so in other words, what I'm saying is that if you do think the dark matter is made of primordial black holes, chi can't be too large and it can't be too small. Now, if black holes form at the QCD epoch, which is the scenario which we rather like and Florian talked about, then naturally speaking, the mass is of order, what is called the Chandrasekhar mass, which is basically one solar mass. The Chandrasekhar mass is the mass associated with white dwarfs. It's 1.4 solar masses. But what's also interesting is that beta m, the fraction of the universe collapsing, is necessarily eta, which is the baryon to photon ratio, which is an important cosmological parameter, which is 10 to the minus 9. It's the baryon asymmetry, the asymmetry between matter and antimatter, so that when the matter and the antimatter annihilate at the QCD epoch, you get the asymmetry turning into the photon to baryon ratio. And so what is the fine-tuning problem then comes down to why is beta the same as eta? And so basically then, the question is, first of all, dark matter and visible baryons have similar mass, but also this raises the question, could the baryons actually generate the baryon asymmetry? Normally speaking, you assume that baryon asymmetry is associated with granunified theory processes as a much earlier epoch. But this suggests that maybe in some way the black holes actually generate the baryon asymmetry. And now, here is the way we think it can happen. So this is another paper with Juan Garcia Bellido and Sebastian Kless. And the idea is this, is that when we focused on a black hole forming, you have an overdense region which collapses and forms a black hole, because it's almost in its Schwarzschild radius even when it stops expanding, if it has an overdensity of order 1. This is incidentally why black holes don't spin, because they don't have to collapse much before they fall inside their Schwarzschild radius. But the point is that when you form a black hole, there's also the matter outside the black hole is expelled outwards. So as the matter collapses, it releases gravitational potential energy into a shell of matter which expands. So although we've not mentioned this so far, you actually, the formation of a black hole forms an expanding shell. So it's rather like a supernova, except it's a primordial supernova. And when you look at this shell, the temperature is so high that you can have baryosynthesis occurring. You have what are called C and CP violation processes occurring, even in the standard model, what's called the CKM model. Now, this is rather technical, and it depends on the fact that you are out of thermal equilibrium, which is important for all the baryosynthesis models. But basically what happens is that the predicted asymmetry, remember chi is the ratio of the PBH density, the baryonic density, it depends on the parameter gamma. Now, I haven't defined gamma here, but gamma is the size of the region relative to the horizon, the cosmological horizon size. So it's a parameter which we know has to be of order 1, but this ratio is automatically of order 5 if gamma is 0.18. So that's saying as long as the size of the black hole is, which is in theory is predicted, if it's right, then you're going to get, you'll explain the black hole to baryon ratio. But then the question is, well, why is beta eta? And the reason is very simple.
We should wrap up at some point because we have lunch.
Yeah, I've got just 1 minute to go, 2 minutes to go.
Okay.
And the reason is very simple, because locally you're generating a baryon asymmetry of order 1. But if the collapse fraction is beta, then by the time the baryons have diffused throughout the universe, you automatically have a cosmological baryon asymmetry of order beta. And so we found this a remarkably beautiful idea, and maybe Florian can say more about this later. If you naturally explain the baryon asymmetry as arising from the primordial black holes, and then the fine-tuning problem has gone away. Now, with that, I want to come to my concluding remarks. First of all, stressing the relationship between PBHs and WIMPs from a historical perspective. You've seen this very complicated diagram on beta M, and the point I've tried to stress is that this diagram is constantly evolving. And I like to make the analogy between FM and the particle that I'm sure you've seen lots of diagrams like the one on the right, which is the WIMP mass against, it's the WIMP cross-section versus the WIMP mass. And so, you know, sometimes one might think of this as a rivalry between the PBH enthusiasts and the WIMP enthusiasts, but both topics have gone through a very similar historical progression. As our observational sensitivity increases for PBHs, these WIMPs, these limits become stronger, and it's the same with particle physics. You know, you get these lower boundaries which come from the particle physics experiments, and it's very similar. And what I would like to say is, I don't think of us as rivals. I mean, obviously, most of you are probably coming from the particle physics side, but really, from my point of view, we need both forms of dark matter. I don't know which of these candidates is primarily going to make up the dark matter, but both candidates are interesting, whether or not they make up the dark matter. I hope that message has come across. We just have to wait and see. And I just want to end up by giving you a sort of 1-minute summary of the history of primordial black holes, because I find it rather fascinating. I've worked in the subject for 50 years. Florian has worked in it for, I don't know, Florian, less time, less than 10 years even. But let me just give you a brief history of the subject. Popularity doesn't mean much. You could interpret popularity in terms of the black hole publication rate, if you like. So it started with Hawking's paper in 71, forming from inhomogeneities. There was interest in them forming the QCD phase transition in 1982. I didn't talk about that specific paper. Then we had the microlensing observations of quasars. Hawking's, you recall, Mike Hawkins was arguing that that was evidence. Then we had the Macho results, which gave an initial excitement when they seemed to get evidence for these black holes, but then it went away a bit. Well, then it was realized that they could form at the QCD phase transition, so popularity increased. Then it decreased when we discovered that the microlensing observations actually only seemed to allow 20% of the dark matter. But then people started realizing that there were these other ranges in which you could have sublunar black holes or intermediate matter objects explaining other observations. I haven't talked about it, but it's conceivable actually that evaporating black holes leave stable Planck mass relics, in which case the dark matter could be Planck mass relics, which are in some sense particles rather than black holes. But we haven't talked about that. Maybe in the discussion session that will come up. But then again, then there was a decrease when all these dynamical and accretion limits came out. So people thought, well, maybe it can't be the dark matter anyway. But now, of course, we've had the LIGO results, and I should say LIGO-Virgo results. And those are what have really, I would say, prompted interest in primordial black holes. But at least I'm glad to be able to end this, our talks on a high. And I would just like to finally thank, first of all, I'd like to thank Marco and all the organizers for inviting us to talk, because, you know, not everyone is keen to hear about primordial black holes if they work in particle dark matter. So we myself and Florian have much appreciated the opportunity to present the case for primordial black holes. So thank you to Marco and all the other organizers. And I would also like to thank Florian, my friend and collaborator, because originally I was going to give these talks on my own, but you know, the English, I'm afraid, aren't allowed to come to France, or at least it's rather complicated if we come to France because of the pandemic. So at relatively short notice, Florian agreed to come and give half the lectures on my behalf in person. So thank you very much. And I know to Florian, and I know all of you also have appreciated Florence being there, because I know he's talking to a lot of you outside the lectures. And finally, of course, thank you to all the students for listening to these lectures, and I hope some of you at least will become interested enough in primordial black holes to contribute to the subject. And so with that, thank you on behalf of myself and Florian. I've now finished and I'll stop sharing.
Thank you actually on our part too. Thank you very much to both speakers. So thank you very much again. We stop here and we go for lunch, and if you have other questions, you can be contacted by email. Thank you very much.